Hi there. My name's Jason. I teach in the Technology Teacher Education program at the British Columbia Institute of Technology in lovely Vancouver, British Columbia. Yeah, technically we're in Burnaby, but it's lovely too. And we're having a great summer right now. It's all-time record heat wave here in Vancouver, which means for most of the rest of the world we're getting pleasant weather. And that's got me thinking it's a great time to go outside and play with some water and pop bottle rockets. Now, it wasn't the heat wave that got me thinking about this, but my colleagues Adam and Steven really got me going on this because let me just find this over here. Adam's been doing this neat thing with thrust vectored rockets and kind of following what's on the BPS space channel. And if you've been following that along, really neat stuff. Watch this thing spin as it goes up there.
Right,
Um,
stop.
the
Now
rocket
something just
motor is all controlled by servos, so it's vectoring and flying along as it goes up there. And actually, some of the technology that's going on in there, it is capable for high school students to do, but if you're teaching junior high or even senior high and you want to do some physics, you want to make some stuff, you want to go outside and have some fun, the pop bottle rocket is one of those things that gets kids to sign up for your class. So let's take a look at a pop bottle rocket and how they're just a little bit different from what you just saw, because gotta admit, that was pretty cool, but so is this.
Hey, quad launch here on three, two, one.
There you go, up at the top, you can see them flying along. And boom, boom, boom. Okay. Here goes the next one. Up in the sky. That one's gone. There you go. You can see them right up over here somewhere, floating around in the air. Now, I haven't put fins on them. I haven't put a nose cone on them. I haven't done anything at all to increase their altitude. I don't have parachutes or a recovery system. I'm just firing them up there like the Chinese space program, and I really don't care where they come down. Um, Mind you, I'm firing pop bottles and not space station components, so it's probably okay that I don't worry about it too much. And down here, you can actually see the mechanism that I'm using. And oh, this wasn't the video I want to show. This one's only at about 70 psi right now, so it's taking a little while to take off. And there it goes up the launch tube, and blast of water coming down right there. We'll take a look a little bit more at how that works in just a few minutes. But let's take a look at what's going on with the rocket launchers. And oh, I don't need to see that again.
Hey, quad
How do I get
launch.
the next slide on here? There we go. Um, I've been doing this for a little while, and in fact, I flipped through my old sketchbook from when I was a student at BCIT, and I found these drawings in here because I built my first pop bottle rocket launcher almost 25 years ago when I was a student in the same program that I'm teaching in now. And I used it with my students, and they had just as much fun with it as I think your students will have fun doing this right now. And so I just want to say there's no right way or wrong way. Well, maybe there's a wrong way, but there's probably not a best way to build a pop bottle rocket launcher. Each of them is a series of compromises. And you can see in some of the designs I put up here, I was really focused on hinges and putting things together. I didn't have a lot of machining experience back at the time, and so I was thinking of things that I could do fairly simply with woodworking and screws rather than going into the metal shop. 25 years changes things up a little bit, and we've got some lovely CNC turned pop bottle rockets launchers for you to take a look at now. But if you go online, I'll give you links to a couple of other sites. There are great sites out there, and they'll tell you other ways to make pop bottle rocket launchers, and they're going to be good too. So this time I started with sketching again, but then went into Fusion 360 and started making. Oh, my 3D mouse isn't working right now. So I started making some of these sketches and designs. So let me turn a few things off so we can get down to what we're really dealing with here. And we'll turn off the fins and the nose cone. Of course, they make it go a lot nicer. Thank you to P. Deagle on GrabCAD for providing the 2-liter pop bottle model. And we'll turn off the launch pin. We'll come back and take a look at those a little bit later on and the constraints. And now you can get in here and you can see a little bit of what we're dealing with. There is a launch tube in here somewhere too. Pop bottle launch tube, we can turn that off. And then we've got the rocket. Oh, that rocket base is what I'm trying to show you. We've got the screws on there. We can turn all of them off. I might leave the nuts in there just because. There goes the pin. And there goes the nuts. And we're left with a base, wooden base in there. Now the base is nothing spectacular. We'll take a look at it in real for just a little bit, but there we go. And this is what we're looking at as the fundamental part of our rocket launcher. And it is just a piece of 1¼ inch aluminum that has been turned down on one end. And this end has been turned, and I'll give you the dimensions that I used in a little bit, but that end has been turned exactly to made up to a, where's my launch tube? Launch pin, launcher. I just turned it off. There we go, launch tube. To a piece of 1/2 inch Schedule 40 PVC pipe. And that Schedule 40 PVC pipe goes up inside your 2-liter bottle, right like so. And that just not only helps keep things stable, but as you launch your rocket, it slides up over top of there so you don't start ejecting water until you get your first foot of acceleration into you. Because what makes these things fly is the air pressure stored inside of them. And by putting some water inside of here, you can, well, first of all, get a much cooler launch, but also you get a lot more energy out of that air as it expands, so you can fly your rocket higher. How much water and all that we'll talk about in a little bit. Okay, now right down at the bottom of this, you'll see that we've got a pneumatic coupling, and I'll talk about these pneumatic couplings right here. And it comes up a 1/8 27 NPT tap. So you're going to drill this out with a Q-size drill bit. Again, that shows up on the drawings that I'll provide you. And then you just drill all the rest of the way through so the air can get up inside here. You apply pressurized air either through a little battery-powered inflator, a bicycle pump, or if you're doing this somewhere close to your shop, you can hook it up into your air compressor and use shop air, and that runs right up in there. Now, one of the neat things about this design is that because the launch base right here comes out, you can take your rocket and you know, your rocket's got these fins and nose cone and all that, and it's kind of fragile. So when you're mounting this, and you got to push it down over the O-ring, and you got to push it down pretty solidly to get over the O-ring, you can take this away from the launch base so that you can do this, you know, wherever your water supply is. You can very carefully measure the amount of water that you've got, and then you can slide that tube right in there, and then you can carry this over to the launch base, flip it upside right, and if you do that quickly, none of the water comes out because your launch tube is now sticking up all the way through the water. And then you can come in here and you can mount it into, in this case, I've modeled it up as a 2x4. And take 2x4s are expensive these days, so take some offcuts that you've got sitting around the shop. And in my drawings, I've shown you that this is a 24mm diameter on the base. So drill out a 1-inch hole. Lovely Canadian bilingual measurements in there. And you can 60mm spacing for either 1/4 or 5/16 inch bolts, whatever you've got. They need to be about 3 inches long so that they come through right here and reach up high enough to support these. Well, we've got the pin in there. I'm a little bit soon. Now, I originally started off just using a couple pieces of aluminum in here, and that works great too. Use some, you know, 1/4 inch aluminum if you've got it, but then I upgraded that and did some 3D printed pieces right in here. And these 3D printed pieces have little grooves down at the bottom so that they catch the launch pin as it comes through right here. And that launch pin, as you can see, comes in and fits right over top of the tab on the pop bottle rocket. So that holds it down. You've got a string tied around this end right here, and you pull it out to the side. Now, you don't want the rocket base to shake or shimmy when you pull it out to the side. So we use a couple more pieces of 2x4 or plywood, and these also raise the base up high enough so that your pneumatic connection right here doesn't get squashed into the ground. And I drive a couple of about 6-inch long big eye bolts right through here, and I stomp on them to press them down into the ground so that this is solidly mounted to the ground. It's easy to pick up and take away, packs into a backpack or something so you can carry it along with a couple of liters of water and your inflator out into a field and entertain yourself or anybody who happens to be around for a little while. And so that's basically what we're looking right here. As you put it together, before you take it out there, you will have to take a little bit of time to get the nuts all tightened down to the right connections right on here, and so that they hold, whether you're using just a piece of metal going across there or a slightly more refined 3D printed piece right in there, you've got to hold them right in place. Now, because it's hard to get bolts that are threaded deep enough and are long enough, on the back right here of this piece, I did counterbore 10 millimeters, half inch, whatever you're talking about, a little bit up into the piece of wood so that you can see that those are counterbored right into the launch base. And so this sits here and it works really nice. Now, one of the things I like about this design versus some of my other designs is that the parts are readily available. And here's some of the parts that you're going to need for this. And I'm doing this all with Canadian suppliers. So if these don't apply to you, I'm sure you'll find similar suppliers wherever you happen to be. So we're using, this is called the number 114 O-ring if they go by number sizes, but it's 13/16 of an inch on the outside diameter, 5/8 inch on the inside diameter, which means that your CS dimension, if you're specifying O-rings, the CS dimension is the ring right around here, is 3/32, comes out really close to 100th of an inch. So you can buy those at Canadian Tire. They're in stock, and Canadian Tire also has some of these other parts. Canadian Tire will also have something called a tank valve. And I'm not quite sure why I don't have the tank valve up here anymore. I went and got it. There we go. Princess Auto has the tank valves. Canadian Tire has the tank valves. And these parts are what's going to let you connect your air compressor up to the system because they've got a Schrader valve on one end. And that means that when you want to do multiple launches, because they've got a Schrader valve on the end, you pump them up to high pressure, and then you can go pump the next one up, and just like a bicycle tire that has a Schrader valve on it, they stay inflated. Now, in order for the Schrader valve or any of these pneumatic fittings to hold together, you're also going to need a, there we go, 1/8 27 NPT pipe tap. So if you've already got one in your machine shop, that's great. But if not, $8. Canadian Tire has them too, and you've got the part number on the screen right there. What else have we got on here? Now you saw that hose connector, and this is what you actually screw into the base of your launcher. And the reason we use this is so that we can use a 1/4-inch pneumatic tube so that when you do your inflating, you're a long way back from the base. And you'll see that I really recommend that you stand a long way back from the base. I say 3 meters, 10 feet, whatever works for you, but you don't want to be right up in there because you've got stored in that pop bottle, when it's all pressurized to 120 pounds with about 1.5 liters of air, you've got somewhere around the same energy as you would get from a 357 Magnum. So yeah, firearms 10 feet. Yeah. No, the issue comes when a bottle starts to get a little bit damaged or worn or overinflated. Most of them can hold 120 psi, okay, but when you start going up to 130, you start, or if you use a Coke bottle, plastic Coke 2 liter Coke bottles burst at less than 100 psi. So you might want to just have a safety setting and tell nobody to go above 90 psi. Set up rules for your class so everybody stays safe. But anyway, you want to have people standing back when you launch. That's just good procedure anytime you're dealing with a lot of stored energy. So these fittings right here, make sure you get the one that you want to check because you just got a 1/8 inch NPT 1/8 inch NPT tap. You want to make sure that you're using a 1/8 inch sized connection as well on here. So there's your part number right there. They've got one that the image looks exactly the same on their website, but it's for the 1/4 inch NPT. And then they've got some other supplies in here that you're going to need. So for instance, nylon pneumatic hose. And this lets you do your inflation from 3 meters or 10 feet back from your launch site. And then you can put a rope on your launch pin so that the person's standing back a good distance. So you can do all of your inflation from a safe distance and make sure that nobody loses their hearing or worse if a pop bottle accidentally happens to pop because they are loud and they send little bits flying. Nothing too dangerous, not too many feet, but you just don't want a kid's head over top of that if the rocket launches early or anything like that. They've got lots of other pneumatic fittings in right here. So if you want to do a head-to-head comparison and pump multiple rockets all up to the same pressure, you can run your compressed air in through here, and then you can run 2 tubes out to 2 different rockets, pump them all up, and launch them together. What else have we got? Yeah, so your tubing right in there. All sorts of different suppliers will have these. My friends who do FIRST robotics competition stuff will recognize this is all standard FIRST robotics stuff that you can get from Andy Mark. So if you're down in the States, actually, go to andymark.com and you'll find all of this pneumatic stuff right on there from a super friendly supplier who's really excellent at dealing with the education market. So anyway, whole bunch of cool pneumatic stuff, and of course the O-ring, pretty important to getting that good seal right on. Oh, I'm still recording. Okay, so hope I captured all that bits and pieces. I guess I'm editing this now. Anyway, this is my first mock-up prototype of the launcher. You can see I used just a couple pieces of aluminum in here instead of the fancy 3D printed pieces to hold the pin in place. This launch base, whatever you want to call it, was hand turned, standard machine lathe. Yeah, it's actually a pretty fun and easy turning project to do, and you can just test fit by hand to make sure that tube is going to fit on there. You can test your O-ring depth while you've still got it on the lathe. Just make sure everything's powered down. Pop the O-ring into the little groove. Just cut the groove with a parting tool, and there you go. You can test fit it, make sure that it's all going to fit together, and then drill out your piece of aluminum, tap the end, do a little bit of a dry pressure test to make sure that you're not leaking air everywhere. It takes a little bit of practice. Use some Teflon tape when you're putting the pneumatic fittings on right here, and here you can see I've got nice bright orange tubing coming off to the side so that we can have our compressor, our inflator, our bicycle pump a long way back from the base. And nothing fancy here. I didn't even put any finish on the wood. This is another shot of it, and you can see the launch pin inserted right here and the string tied to that. That lets your whoever's doing your launch stand back a good distance from it so that in the event that something goes sideways, everybody's nice and safe. Here you can see a couple of the launching bases drilled and tapped. One, I put the tank valve, the Schrader valve, straight into here. So if you had a really long cord on or hose on your tire inflator, you could just hook that directly onto there. Like I say, personally, I prefer to have a 90-degree connection right here and pneumatic tubing coming off from right here so that you're definitely a long way back. This was my second prototype, and as you can see, it's all set ready to go. A little bit of paint and laser etching makes it come out looking pretty nice. A couple of eye bolts right here to drive spikes down into the ground. And yeah, this one's been tested. Here's my setup. So like I say, all of this fits into a backpack, and so you can take it out in the middle of a field somewhere. Lay two pieces of wood down right here, and then put your cross piece on it. As you can see, we're flying for space Y today, one letter better. With a little warning reminding people to stand back. These eye bolts are going to go through these two holes right here, and they should dig into the ground. Depending on your soil type, you might want to use something a little bit different. And there they are on their way in, and you can either screw them down, or I like to stomp on them a little bit. Make sure they're in there nice and snug so that when you give that launch pin a good pull, everything stays pointing upwards. There we go. Now for filling your bottle, you can take this and do it anywhere. You take the two, once you've got the right amount of water in your bottle, you take the entire launch assembly, push it down inside. Got to really wiggle it past that O-ring. You want a nice snug fit on that O-ring because we are going to pump this up to a pretty good pressure. And here you can see that we've got a long piece of 1/4 inch plastic tubing that comes out right here, and then I just used a pneumatic adapter right here to put my tank valve right there and hook it up like so. And there you go. Now it's all hooked up and it's resting in right here. And then you can take the launch pin and insert the launch pin about like so. You can see it fitting over top of the flange on your pop bottle right there. The 3D printed pieces need to have a little bit of clearance space cut out on them. And then hook up your compressor, walk back a distance, and everything should be ready to go. So here's a good example of us all standing back a nice distance. I took my nephew and niece down to the local park, actually behind Van Tech Secondary here in Vancouver. And as we were launching them, we found that people were coming out to watch what we were doing because it's really cool.
Three, two, one, pull. Big pull.
Okay, now this is slow motion, right? Because when it runs fast, you really don't see it go. But you can see it goes a long way up, and even in slow-mo, you know that thing's just hanging there. Now you'll notice that the pop bottle is just spinning wildly. And you'll notice the point that this happens in a lot of the videos, that where it starts to spin wildly is just follow that launch. And it comes up, and you can see that it goes off the launch tube, then it comes up right there, and oh, I can't quite grab where it goes off. But there's a space right there where you see that big poof coming out right there where you actually run out of water. And then the air that's left inside just comes out as one big rush, and it gives it this massive acceleration kick. It's almost like having a second stage go off. And when that happens, how it interacts with the water and that where that last little bit of water is coming out makes it highly random where it's going to go. And here we go. I'm going to loan my nephew to the Chinese space program so that he can catch their random rocket boosters when they just let them flop back to Earth anywhere. Oops, he missed it. Oh well, I guess the village got wiped out somewhere. Now here's my colleague Rory. He took one of these home and was experimenting with it. And he did me the great favor of creating a video that shows what happens if you don't pay careful attention to the pressure. Now the other thing you'll notice is that this bottle has a little neck right in it right here. This is similar to the Coke bottles. They tend to burst at lower pressure. And I assure you that what you saw right there, that was typical. I've burst one or two of these before. The sound you heard there is in no way representative of what that actually sounds like in real life. And I guess the best way I can describe it as that Rory reported to me that a few moments after that pop bottle exploding, there was a police cruiser driving slowly down their street looking for where the report of the gunshot had come in from. These things are loud when they break, and it's not a great idea to go around breaking them. So keep the pressure carefully controlled. The highest I've gone is 130. That showed some damage to the pop bottle. I've seen burst tests online that go up to 150. I had one that survived at 130 but showed some permanent damage, and I destroyed the bottle immediately. I've done multiple launches at 120. But at the same time, I've had a Coke bottle break at 95. So when you do this with your students, make sure that you do a couple practice runs and you're comfortable with setting your pressure. All I'm going to tell you is that you do want limitations, and if you set it too high, the pop bottles will fatigue before you get a lot of flights out of them. Here's what a little nicer flight looks like, and beautiful sunset. Just watch the water catch that as it goes up there. Now, um, the nice thing about East Vancouver is the pop bottles all have deposits on them, so if you can't find them again, I think you found that one. But if you can't, then we've got people who run around through the go through the neighborhood picking them up, and they get 10 cents for each bottle that they take back. But don't litter, okay? So here we go. This is a super slow-mo shot of two bottles taking off. Little different amounts of water in each of them. You can see the strings go taut, and I was trying to get them at about the same time, but I'm recording this at 960 frames per second. So you see that we're within a few milliseconds of each other. Now, a couple of things to note about the launch. You can see right up to there, not very much water is escaping until you get off that launch tube. So you're just letting the air expand. Then you get this little bit of a burst coming out, because when it comes off the end of the launch tube, the compressed air right inside here kind of forms a little bit of a hole, and it can blast right through there. You get this little burst of air, and then this great, beautiful stream of water coming off right there. And look at that. We probably need some fins on there. You can see it starting to curve. And right there, doesn't that look like it's a shock wave and that it's breaking the sound barrier or something like that? What you're actually seeing, that's where the water's run out, and now we've got air coming out through there. Now, as you watch this stream of water, you'll see that it's still going upwards, which means that right now the rocket is moving faster upwards than it's ejecting the water out the back. Okay, so think about that. That water is compressed and being pushed out the back of the rocket really fast. But at this point, the rocket's going upwards faster than it can squeeze the water out of there. And then, so you've got this water coming upwards, and then this poof of air comes out the back and hits it. And at that point, there you go. You can see the compressed air coming out. Now, the neat thing is we're dealing with a lot of kinematics going on here, but we've also got some thermodynamics. You can see that we actually have water vapor inside here. And when the rockets come down, they're going to have water vapor inside. And basically, my niece thought this was so cool. It was a cloud. And she said, oh, it's like we shot them up in the sky so high that they went and caught a cloud. And that's not the thermodynamics explanation, but it's could be worse. And there we go. And there you can see without the fins on it, that stage just induces a little bit of uncertainty in its flight path right there. Now, the other rocket, you can see the water level going down in that one gradually, gradually, gradually. It had a little bit more water in it, I think, came out a little bit slower, hits that burst point at a slightly higher altitude, and away it goes. And there you can see that the water is indeed still going upwards. And then, of course, gravity takes over and it comes downwards. And somewhere in there, you can actually see the rockets tumbling around way up in the sky towards the end of the video. There they were off over there. So they got pretty small. A lot of fun stuff. here's a super slow-mo of the launch, and wanted to check and see if there was any interference between the launch pin and the restraints right here. So this is the prototype again. Um, Hand-turned piece of aluminum, which is perfectly fine. Chunk of wood right here, just 2x4 offcut, nothing fancy. And here we go. We give it a good tug. And again, this is like 1 millisecond resolution right there. You can see it start to move right there. It takes, if you give it a sharp tug, 1, 2, 3 milliseconds roughly for that pin to clear the launch. And then that rocket, this was at about 110 psi of air pressure in there, starts coming up right there. You get a little squirt of water where it goes over that base, and then it's gone. You get that burst where it just air comes out where it first comes off the top. Beautiful blast of water coming out there where the water jet hits the launch tube, and then continuous stream of water as the rocket accelerates upwards and out of the picture. So that's what it looks like continuously as you go along right there. Lots of fun doing this on a hot day. And I got pretty wet during that launch. Now in another video, I'm going to show you how I went about making the water rocket launcher tubes, or the water base, whatever I call it, the metal bit. But before I do that, I want to assure you that I am by no means a world expert on water rockets or pop bottle rockets or whatever you want to call them. I'd like to point you to some resources, however, from people who actually are rocket scientists and have put some time into this. And this first one is out of the UK. The National Physics Laboratory in the United Kingdom has come up with a really amazing resource on how to do this with your students. Okay, they've got water rocket simulator software. They've got posters for you, booklets. The booklet covers the physics, and my goodness, you know, take some time to go there and read that, and you'll have that extra 1 day of information that will put you 1 day ahead of the kids. So you'll seem like a genius when you're talking to them about this, even though you're more of a brain surgeon than a rocket scientist, right? Okay, now if you are really getting into this and you want to go for the extreme, or you've got that really keen kid who's just can't quite get enough of it and says, but why does it do this and how does it do this? There are actual genuine research papers published online where they can go in and they can do genuine research to their heart's content. And here you go is a link to one of them. Cedric Gomez published in the American Journal of Physics. So genuine scientific publications saying that this is really cool. That's one link right there on the approximation of DII water rocket dynamics, including air drag. So you can Google that, and there's all the links and information that you need if you've got someone who wants more information. However, there are people who've taken some of these publications and done some really neat things with it. They've come up with simulators that let you come in here and say, okay, I've got a 2-liter water rocket. I'm putting in 0.8 liters of water at 120 psi. Works in metric too. You just have to, use and indicate what units you're using. You tell it the nozzle size. And what's really cool about this one, it kind of stuck with the nozzle size with my launcher design, but there are other designs. And go to that Air Command Water Rockets page, and you'll see they've got a whole bunch of information on nozzles. But you can come in here and say, well, what volume should I use? So I can say anywhere from, let's go from 0.2 to 0.6 liters of water, and you submit your simulation, and it comes up with this prediction on how it's going to do. There's 200 milliliters of water up to 600, and you can take a look in here and you can see where your apogee is going to be, and you can see right in here that it predicts that your maximum altitude in this situation is going to be 77.8. So if you're trying to figure out how much water to use, 77.9 431 milliliters of water is going to do better than 600 or 200 in this design. So when you get that all plotted out right in there, it gives you some more information about it. And then you can come back and you can rerun your simulation and say, okay, well, I am going to use 0.431. And let's submit that simulation again. And this time, because I only put one value in here, it's going to plot out your altitude over time, your velocity. This is predicting that you're getting up to 80 meters per second. That's insane because 10 meters per second is 36 kilometers per hour. So this is predicting that you're going to get somewhere over around 250 kilometers an hour on your launch, which for a pop bottle is pretty cool. That's why they keep going upwards, I guess. Your acceleration is going to be massive immediately, then you're going to slow down, and there your thrust, you can see, is going to last you up, what's that, approximately 30 milliseconds. So that's kind of, and then kind of drops off right there. So you'll have to take a look at that. Different simulators have different degrees of accuracy and model the transition from blasting water out the back to blasting air out the back slightly differently. So you may find a different simulator that provides more accurate results or less accurate results. However, if you want the ultimate guide in online pop bottle rocketry and people who just make me go, oh my goodness, how far can you take this? These guys and gals at Air Command Water Rocket have taken it about as far as you can go, and they've documented it all for you. And just look at the resources down the side. I said they would talk about different nozzle designs. So they've got a whole section on here. And so all sorts of different nozzles that you can put into the design of your rocket, how to make fins, different styles, flat fins and round fins, and how to connect them. Uh, they've got everything that you could possibly look for in here, right up to adding drop-away booster rockets. Okay, splicing bottles together so that you can get more altitude out of them. And if you go over to their YouTube channel, somewhere in here, there's a link to their YouTube channel. You'll find that they've made carbon fiber water rockets that they've fired up to like 3 kilometers in the air, and they've taken just plain old pop bottle rockets, and I think they've gone up to something like 750 meters, doing wild and crazy stuff. So Air Command water rockets, if you're interested in this kind of thing, yes, you can take it to the next level, and there's people on here guiding you and suggesting different ways to do it. They've got different launcher designs, but for what we're doing in terms of education, I think I'm pretty happy with this design, and it is actually kind of a neat tech ed project. We're going to be doing it so that students will get a blank that I've made in the CNC machine. They will measure that, create their own drawing, take it into the machine shop, turn their own by hand, and then in another class, we'll do all the launching and electronics. We'll probably make a data logger to record their altitude and time, and we'll program that. And then who knows, perhaps in their CNC course, they'll end up creating the CNC lathe turn version of their launcher and kick out a class set of them. Anyway, I hope you've enjoyed this. And before I go, let me come back here. I need to give you one more thing before I take off. Where is the drawing? Okay, it would be remiss of me to leave you without some dimensions. I promised I was going to leave you with some dimensions right there. So there's that 114 O-ring goes into that slot. You just cut that slot with your parting tool. And here's dimensions all in millimeters. So, yeah, I don't care what you drill it out with right in here. I found a Q tap drill worked really well for the 1/8 inch NPT taps. Start with a piece of 1.25 inch aluminum stock, about 4 inches, 100 millimeters long, face off the ends, and away you go. I started by turning one end down to diameter, then flipped around, turned the other, and then drilled it, tapped it all out. But I'll show you more about that in another video. Have a good time. 3, 2, 1, lift off.